webinar. IMSc number theory webinar is Professor Ritubroto Munshi from ISI Kolkata, and he will be talking about arithmetic correlations. Professor Munshi.
Thank you. So, thanks to the organizer for a kind invitation. So it's always a pleasure to give a talk at IMSc. So today I'm going to talk about what I'm calling arithmetic correlation. So it's basically about, let me see, maybe I skipped one. Okay. Yeah, it's about sums like this. So suppose you have two arithmetic sequences, an and bn, and you want to understand the sum an times bn, where the sum, a priori I'm saying that it's up to infinity, but we'll soon restrict the sum in a dyadic segment. Okay, so the sequences that you may be interested in are the following. Like, you can take one of them to be 1 and the other to be n to the power it, for example, here. So here you're basically interested in, so if you're trying to bound, say, zeta of half plus it, then this is the sum that you get. Okay, and then if you are, you can also have an equals to 1 and bn equals to chi n. So this is the type of sums that will appear when you are looking at the Dirichlet function, and if you want to bound the L half chi, right? Or you may be looking at an to be chi n, bn to be n to the power it. This corresponds to L functions where you are interested both in the t aspect and the level aspect for Dirichlet function. All right, or you may take an to be coming from a higher rank group, like it may be a Fourier coefficient of some modular form, say lambda fn, or maybe a Fourier coefficient of the mass form. And so if an is lambda fn and bn is n to the power it, so lambda fn for me are normalized Fourier coefficient. Then here this type of sums appear with an equals to that and bn n to the power it. If you are interested in the t aspects of convexity, for example, so if you're looking at half plus it of the modular form or the mass form, okay? So you want f to be fixed and t goes to infinity. Or you can also take bn to be 1 and an to be lambda fn, and say you have some level or weighting f, and you want to understand the size of the L function. So then such type of sums appear. And the next one is when you are looking at the twists of DGL2 form. And the sixth one is quite interesting. This type of sums where you have lambda fn e of root nx. So here e of z is as usual e to the power 2 pi I z, right? And this type of sums appear when you are looking at GL2 analog of the Dirichlet divisor problem. Suppose you were looking at sums of the form lambda fn, where in you have a sharp chord, n goes up to x. Then if you want to bound it by something over here, and then usually you get an expression by applying the Voronoi summation formula or something, you get an expression over here, which involves lambda fn e of root nx. Okay? And the last one is also interesting. This type of sums appear when, so here lambda pi n1 are the Fourier coefficients for pi GL3 form. Okay, and so if you're interested, for example, in showing, so you look at the L function for this GL3 form, so it's a degree 3 L function. And if you're interested in showing that there is a critical zero of this L function, so there is 1, 0, at least 1, 0 on the central line, then you get sums of this form with the Fourier coefficients of GL3 form and twisted by e to the power e of n to the power 2/3. Okay, so that's what's called a nonlinear twist. Okay, so such type of sums are common in analytic number theory, and it appears in many places, like in subconvexity problem, or if you're interested in the Dirichlet divisor type problems, or if you're interested in say critical zeros, something like that. Okay, so we'll have
Ritubroto, there is something, then subscribe now, or something has come. If you can enable.
Oh, sorry. I think you just
Thank
keep
you
on coming. Yeah. Sorry. Maybe it will come back in 5-10 minutes again. Sorry about that. Yeah.
Okay.
Anyway, so we'll have some standard assumptions about this arithmetic sequence. The first one, as I said, I'm not interested in infinite sum. I'm going to look at a dyadic range. So I will have a parameter n, and my an and bn's are going to be, or at least one of them is going to be 0 outside this range, right? And we are also usually will have that these coefficients an and bn, or the arithmetic functions, are not really large. They are bounded by some n to the power epsilon. Okay, and you may not. So for any arithmetic sequence, you probably will not have this available to you, but at least in the L2 sense, you need it. Okay, so if you look at absolute value of n square n summed over of size capital N, then it is bounded by capital N to the power 1 plus epsilon. So, okay, that's the L2 sense bound for an and bn. Okay, and we are also going to assume that one of these sums an or sum of bn is small. Okay, so that really means that if you have this size restriction, that really means that trivially they are of size n to the power 1 plus epsilon. But we're going to assume that one of them is there is some cancellation, and we have, that's it, bounded by n to the power 1 minus delta. Okay, and then the standard definition of correlation is the following. So you take the or it's a formula for correlation. So you have this sum. So you're taking the inner product of these two vectors and take the average, and then you subtract the mean. Okay, and since one of the mean is small, so this product of these two means is bounded by n to the power minus delta. So the correlation is basically given by s by n. And so if you want to show that the two sequences are independent, what you have to show is that this sum is bounded by n to the power 1 minus delta for some delta positive. Okay? However small, it doesn't really matter a priori. Right? Okay, so that's the problem. Okay, so basically the philosophy is, if you believe in Riemann or Lindelof, that if you have two arithmetic sequences which are coming from two different sources, then they're supposed to be independent. Okay, if they're oscillating. Okay, so that means you'll expect something like this if they're coming from two different sources, like we had in up here. Yeah, like we have over here. Okay? And actually, the Riemann hypothesis will say that that Sn, in that case, if n is of size capital N, then it should be bounded by n to the power 1/2 plus epsilon. Okay, so now I'm going to present a template which I'm going to use to get some results in this direction. Okay, so what is the idea? The idea is that we're looking at, we're studying the correlation, or looking at the inner product of two arithmetic function. So let me start with the space of all such functions. So V is the space of all such function. Okay, it's a vector space of dimension n, roughly speaking, because we have n many integer points in this range. Okay, and the sum we are interested in can be written as the inner product of A and B bar. It's the usual Euclidean inner product. Okay, and suppose now we have an orthonormal basis of the space. Say B is the orthonormal basis of the space V. Then this inner product can be decomposed and can be written in this form. Okay, so where V runs over all the basis elements, and you have the inner product of A with the basis vectors, and the inner product of B with the basis vectors. Okay, so that's another way of writing S. And then so for individually for each of these pieces, we are going to analyze them using summation formula. Okay. So for example, so if you look at this particular sum over here of inner product, that is basically given by this sum, then there will be some sort of a summation formula, which is we have to, it will depend upon what type of basis vectors you have picked. And I'll tell you about some standard basis vectors. And then we'll have some summation formula which will relate this sum with a dual sum, which will have a different length. I'm calling it n star, and it will have a different type of arithmetic sequence, a star n, and there will be a different type of basis element, psi v star. Okay, so soon I'll give you some examples, and then it will become clear what I'm talking about. Anyway, so once I apply this summation formula to both of them, then the original sum get transformed into something like this. Okay, so this is the length of the one of the sums is the length of the other sum. If A and B are really different, then you expect that the dual sums are different. So n star and m dagger are probably not of same length. Okay, and then the last step is, or maybe the penultimate step, is that you apply a Cauchy inequality. Okay, so you take one of the sums outside. So here I'm taking the n sum, I'm taking it outside. Okay, so this is where I'm using the L2 norm of this a star n is bounded by n star. Okay, so they're like L2 normalized sequences. And then here I have what is remaining from the Cauchy inequality. Okay, and so at this step I'm getting rid of the coefficients or one of the arithmetic sequences a star n, and so I can open up the absolute value square and apply another summation formula at this level. Okay, with respect to n, because it's kind of free. Okay, and then okay, that's the last step. Okay, applying the summation formula, we may have to estimate some character sum where you can use Deligne or something, and you get an estimate for S. Okay, so that's the standard template that I'm going to use, and it seems to work in many situations, as we'll see. Okay, so how to get the basis elements? Okay, so of course this is just basic linear algebra. So if you have an orthonormal basis, then you have this is the relation between the basis vectors in an orthonormal basis. Okay, so or the corresponding matrix is an orthonormal matrix, and you have this relation. Okay, so that so if you sum over the basis elements, okay, of psi v n and psi v m bar, then it is equal to 1 if n equals to m and 0 otherwise. Okay, so this is the Kronecker delta symbol. Okay, and basically this is the relation that is what is important to us. Okay, so once we have a collection of functions psi v n and psi v m psi v n's which satisfy this relation, then we can write our original sum s in this form. Okay, and thinking about it as an orthonormal basis is a way of visualizing this procedure. Okay? So this is what we should be mainly looking at, trying to find out functions for which we have such a relation. Okay? And one source of this type of function is the usual circle method or the delta method. Okay? And let's see, next I'm going to tell you a little bit about the circle method. So in the classical circle method, what you do is you try to show that the psi v n's can be taken as trigonometric functions. Okay, so the trigonometric functions are the usual harmonics which come from the circle group. Okay, and one can try to generalize it, and one can try to replace the circle group by higher rank groups and try to use the harmonics of that higher rank group and come up with different forms for expansions of delta n. Okay, and so here is one usual delta method. This is just the skeletal remaining of the formula. Okay, so this says that okay, you pick your q's ranging up to square root of n. Okay, you are interested in the range between capital N and 2n. So your modulus is going up to square root of the length. That's q, and then you have a modulo q, and a and q are co-prime. And then you have E of an by q and E of am by q bar, And this is more or less, this is just an approximate statement that it's more or less like the Kronecker delta symbol. Again, Ex is e to the power 2 pi x. Okay, that's a standard thing. And so this basically implies that I can pick, so my V is going to be this pair A and Q, where Q is ranging up to square root of n, and A is running modulo Q, A co-prime with Q. That's my collection of basis vectors. And for each basis vector, each basis vector is given by this. So 1 by square root of n, that's the general normalization, E of A and Q. And then this formula is basically saying this is an orthonormal basis. Right? Okay, so the circle method gives you circle method is a natural source, or is actually a way of getting an orthonormal basis of the space. Okay, so now this is the real formula due to Dirichlet and advantage. So here I just the previous slide I just wrote this part. So there will be some analytic function hanging around with it. So you have to take care of different issues. And that Q is a priori up to you to choose. But the usual thing is you pick your Q to be like square root of the length you're interested in. So it's called the length of the equation. Okay. So I'm not going to write down the formula for H. The nice thing is if you pick your Q to be like square root of n, then it means that this function is nice. Okay. In the sense that if you take the derivatives of H are not that big. Okay. And here is another version of circle method. This is the Klosterman's formula. And here you'll see certain difference. So if I put a bracket over here, it will probably can relate it better with the previous formula. So here, this part is basically what we had over here, more or less. But now the main problem is here, this is the function which corresponds to H. The problem here is that this A, which was not involved in H, is now involved here. So that's a big issue in the Klosterman circle method. And this 1 by AQ is same as the 1 by Q that you have over here. Okay, so that's related. So this is a more classical form of circle method due to Klosterman, with some certain drawbacks, where the Dirichlet advantage takes care of certain drawbacks. So the main problem in DFI is that this function H is not really explicit. It's really oscillating, and sometimes you really need to know a lot about this function. Whereas here, this function is completely explicit, though the arithmetic parameter A is involved in there. So here are two different ways of getting those basis vectors psi v. Yes. Okay. Okay, so now let's look at one basic problem. So we're going to use our template and study this particular situation. So we're starting with the modular form F. So if you wish, you can just stick to the modular form delta, which is the Ramanujan discriminant form. And that the form is going to be fixed in the analysis. Chi is a Dirichlet character, modulo P, and I'm going to take P going to infinity. That means P is getting larger. Okay. And we want to study the sum lambda fn chi n, where small n is like capital N. Okay. And so if you're wondering what is the relation between capital N and P, so here is the observation. So I'm going to look at smooth sums. Okay, it's not a sharp cut. So the weight function over here is not really the issue. So we should put a smooth weight over here like this, which I'm ignoring. Anyway, so if you have smooth weight, the nice thing is that if n is large, for example, if n is slightly larger than p, so probably you have to take n to the p to the power 1 plus epsilon, say, then if you just use the functional equation of this GL2L function, LSF twisted by chi, then you already have a non-trivial bound. So you can show that it's bounded by n to the power 1 minus delta, where delta will depend upon epsilon. Okay, the bigger the n you pick, better is the bound that you get. Okay, but we'll be interested mainly in the complementary range. So we'll be mainly interested when n is less than p. Okay, and more importantly, we'll be interested in when n is really of size p. Okay, that's the sum that comes up when you are dealing with the subconvexity problem of this L function. Okay, and of course, if capital N is the length of the sum is very small, then the problem is hopeless, because then you really need something like the Lindelof hypothesis to tackle the problem. All right, so now I'm going to blindly apply the template that we have to this sum, right? So let's see what happens. Okay, so I'm going to start with the sum lambda fn by n. N is of length n. I'm going to take n to be p for simplicity. Okay, and so now I'm going to replace it by those two sums. So I'm going to apply the delta method. Okay, so I'm going to pick my q to be of size capital Q, which is square root of the length of the sum, square root of n, right? And then I'll have a sum over q, and then sum over a modulo q. Then I have a sum over n lambda fn e of a and q, and then you have a sum over m of length n phi m minus am by q. Okay, so I'm ignoring the h part. Okay? So that you can ignore, because I'm picking my q to be like square root of n. Okay, so there is an issue where, because small q will actually range from 1 to capital Q. When small q is small, then you have to take care of the oscillations coming from this function over here. Okay? Otherwise, it's not an issue. Okay, so here it should be divided by n, because that really counts for the number of basis vectors that you're introducing. Okay, so this is my sum S. So S has become this after application of the circle method, or the first step of this template. And now, as I said, that I'm going to use the summation formula. So there are two sums that we need to analyze. One is this, the other one is this one. So let's apply the summation formula to the first one. So we have lambda fn p of n by q. N is of size n. So this is a perfect candidate for the Voronoi summation formula. So the Voronoi is going to transform it to something like this. So the dual length is going to be, so f for me is fixed. It's like the delta, right? So it's going to be square of the modulus here. So it's q squared by n. Okay, but I pick q to be root n, so it's going to be just 1. Okay, so the dual length is just going to be 1 here. You have lambda fn, okay, and then you have here e of minus a bar n by q, and then there will be some Henkel transform and all that of the weight function. But since the weight function is not really oscillating, the Henkel transform will not matter that much, right? Okay, so that's one sum. Okay, now let's look at the other sum. So this is called the Voronoi summation formula. Yeah, so I must say here that note that since the sum starts with a length of size capital N and ends with a length of size 1, you have a saving. The saving is square root of the initial length by square root of the final length, which is basically square root of n, right? Right. So if you go back to this step over here, when we apply the first step in our template, if you trivially estimate this, you'll get it's bounded by n squared. Okay, so you wanted to show that the sum you started with is bounded by n to the power 1 minus delta. After the first step, it has blown up and has become of size n squared. So your job is to save n and a little extra. Okay, so the first step, by applying the Voronoi, I have saved square root of n. Right. Now let's look at the next sum. Okay, so here it is. So I'm going to look at the sum over m of size n, chi m, the Dirichlet character, minus am by q. Okay, and again, this will get transformed into some sum m, whose length is going to be bounded by, so now this is GL1, so you have to find out the modulus. The modulus is q times p. So it's p times q divided by n. And I picked n to be p, so it's like q. Right. And the character sum that I get here is the beta modulo PQ chi beta E of minus A beta Q E of beta M by PQ, right? Okay, so now and really evaluate the character sum. So if you look at the character sum, so there are two parts. One part is modulo P, so beta modulo P chi beta E of minus A, sorry, the A is not there. It's okay. Beta M Q bar by P. Okay, so this is going to be just chi bar of M chi Q times the Gauss sum of the character chi, which is anyway fixed. The other sum, modulo Q, so if you look at beta modulo Q, it's going to be E of minus A beta plus M P bar beta by Q. So this is going to give you a solve for A. Okay, so A is going to be congruent to M P bar modulo Q. Right. So if you go back, so here this last line, it just says that we are able to evaluate A modulo Q. Right. So if this was the original sum, I have applied summation formula to the n sum and the m sum, and I've been able to get what A is. Okay. So let me let's go back and find out what exactly I'm saving over here. Okay. So by the usual thing is by Poisson, the saving by Poisson is again square root of the initial length by square root of the final length. So square root of n by square root of q, but q is root n. So it's n to the power 1/4. But since A is getting evaluated, you are also getting a square root of q saving over here. So you have another square root of q saving over here. So that is basically root n, right? So here also you save root n. Okay, so in the first step, when you apply Voronoi, you save root n. Now we are also saving root n. So together we have saved n. Okay, and now we have this sum. Right. So now we have a sum over q of size root n. A got evaluated. You can ignore n. N is of length 1. And then we have a sum over m of size. Yeah, m is of size q, which is also root n. Okay. Sorry, that. Yeah. Okay. Now what else do you have? From the Voronoi, I had this E of minus A bar n by q. Now A I know is m p bar modulo q, right over here. So I'm going to write that. Yeah. So I have here E of m bar n q. I have a p thing. Okay. And then basically you have a chi m and something. Okay. So this is the only part which involves both m and q. Okay. The other parts only depend either on m or on q. Okay. So this here, what you get is called a bilinear form. So I'm going to just ignore this and say alpha m beta q. So these are some things which are only depending on m. There's some things which are only depending on q. But they together appear in this Klosterman fraction thing, E of m bar n p by q. Okay. And for this sum, we have a large sieve inequality, and that's due to differential advantage. So this is exactly the sum we're looking at. The lengths of both of them for us root n and root n. Okay, and if you look at this, so if you ignore this part of the bound, then you get the trivial bound. Okay, and so this is the saving that you get by applying their result. In our case, both capital M and capital N are root n. So we are saving here root n to the power 1 by 58, which is n to the power 116. Okay, So the bound that, so we had already set capital N, and now we have set capital N to the power 1 by 16. So finally, we're able to conclude that S is bounded by, so that was our bound after the first step of after applying circle method, minus 1. That's what we saved from applying the summation formulas, and the sum over A minus 1 by 16. Okay, it is N to the power 1 minus 1 by 16. Okay, so that's how we can show that the Fourier coefficient of GL2 and the character and the Dirichlet character are independent of each other. All right. Okay, so from here we really don't get a very strong bound for this. So this gives you a bound for the L function of S twisted by chi. Okay, and the bound that you get is just p to the power 1/2 minus 116. Okay, so that's the bound that you get. It is not that strong, but it's non-trivial, right? But there is a better way of using the template. Okay, so that's what I'm going to do now. And the trick that I'm going to use is called mass transfer. Okay, so I'm going to again apply the GL2. I'm going to apply the delta method to this lambda f and chi n, and now we'll get a better bound. Okay, by applying a trick. So this is the sum that you want to estimate. Okay, and so this is like before using the template, we apply a trick and then the template, and it gives you a much stronger result. Okay, so what is the idea? All right, so I'm going to first introduce a dummy variable. So I'll call it L. All right, so L will be of size L, lambda FL bar. Right? Going to put N, and so N to me is going to be of size NL. M is going to be of size N, lambda Fn by M, okay, and delta of N ML. Okay. Okay, so delta N ML just means that N is equal to ML, otherwise it's vanishing. So if N is equal to ML, then so this basically says that this is equal to L lambda F L bar, and then you have a M of size N and lambda F M L by M. And suppose if you, for the moment, if you assume that the Fourier coefficients are multiplicative, then this lambda FML will be lambda FM times lambda FL. And then with lambda FL bar, you'll get the sum of L of size L, lambda FL bar square, and then the original sum that we have over here, exactly this. Okay. So this sum over here is not exactly this, but it comes with a multiplier which looks like this, right? Right? And so that is more or less of size capital L, because F is fixed, right? So we know that the L2 norm of the Fourier coefficient is, on average, the Fourier coefficient L2 average is of size 1, right? So if I divide this thing by L, basically, then this is more or less the sum that we started with. Okay, so instead of the original sum, we did what I call a mass transfer, and I have increased the length of one of the sum and split the other term into two parts, okay, M and L, right? And now I'm going to apply the same template. So I'm going to apply a formula for the delta NML over here. So I'm just going to apply the same circle method, right? Okay, so yeah. So if you take a trivial bound over here, then you'll see that this guy is bounded by n squared L. So you need to save NL. Okay. So here you need to save a little more, okay, depending upon the L that you pick. All right. So now this is the sum that you need to analyze. L is of size L, lambda FL bar. Okay. So Q is now bigger because the equation is of size NL. So Q is going to be of size square root of NL. Okay. A modulo Q. Okay. And then you have n of size NL. So I'm just going to drop my F over here. Okay, so lambda n. Right? And oh yeah, but one thing. I have to go back. I have to reduce the modulus in some way. I forgot about that. Yeah. Sorry. Yep. Okay. So before applying the circle method, what I'm going to do, so this is what I'm trying to detect, n equals to, I'm trying to detect a, sorry. Oh, yeah. So I'm trying to detect n equals to ml, right? And so I'll do it in 2 steps. Okay, so first I'll apply a congruence that n is congruent to ml modulo p. So I'm using it because p is the modulus of the character chi that's already here. So mod p harmonic is already present in the problem, and that's what I'm going to exploit. And then I have the equation n minus ml by p equals to 0. Okay, so this is an integral equation because the first condition says that this is an integer, right? And so since it's an integral equation, I can use my delta method to detect that, but my modulus is now going to be small, right? Because the length of the equation is small. The length of the equation is NL by P square root, right? All right, and again, suppose you take n to be size p, then it is just square root of L, right? If n is equal to p, that's the length I'm interested in. Anyway, so now I have the formula. Okay, so I have my L sum, lambda L bar, and then I have Q running up to capital Q, where capital Q is that. And then I have a, but the a will not be only modulo Q, it will be modulo P times Q, because I'm also going to detect n congruent to ml modulo P by additive characters. Okay, and then I'll have the sum over n of size NL, lambda n, and here I have E of an by PQ, and then I have a sum over n chi m, E of minus am by PQ. Right, so that's our job is to save NL and little more in this sum over here. Okay, so again, we apply Voronoi and apply Poisson. Right? Okay, so let's see. So if you apply Voronoi, so the length here, the dual length will be again p square q square. So it's
Ritabrata, you have a question. Would you like to take the questions in the end or in the middle of the?
No, it's okay. You can take it now. Yeah.
Vinay, you can ask your question directly.
Okay. Hello. So
yeah,
I just wanted to know if this level lowering is crucial to the argument, or can we win even without doing this?
No, it's crucial. Yeah. So the first part I showed that what you get without level lowering.
Yeah.
So now I'm using the level lowering thing, and you get something much better.
Okay. Mass transfer alone is not enough.
No, it's not enough.
Okay, okay. Thank you.
Yeah, I'm doing the mass transfer just to increase the length of the sum, and so that I can do the level loading.
Okay.
Yeah.
Thanks.
But really speaking, I don't know. Maybe sometimes someone may come up with some argument which works without this mod p. Okay, these things are happening.
Okay.
So I'm not sure. Yeah, if you should try and find out whether it can work that way.
Okay, sure.
Yeah.
Thanks.
Yeah, I tried. I failed, but it doesn't mean that it doesn't work.
Okay.
Yeah. Okay. So yeah. So the dual is PQ squared by NL. Okay. Yeah. So maybe I'll just keep it like that. Yeah. So this is actually becoming of size P if I'm using this. Okay. So that's the yeah. And then I have a lambda n E of minus a bar n by PQ. This remains the same. The Voronoi. Okay. So the saving here is much less. It's not square root of n anymore. is just square root of L. So saving here is square root of L, okay? Because N and P are of same size. Next, I apply Poisson, okay, to the sum here. And now we have some better bound here, because our dual length is going to be PQ by N. So it's going to be just Q, right? And let's see, I'll just write down what we get in the character sum over here. Okay. Okay, so I'm not, yeah, inside just 20 minutes. Yeah. So after doing all this, this is the sum that you arrive at. So we have a lambda L bar, and then I have a lambda N. And then, so here again, I have evaluated. So R P bar. So what is R? R is M. Did I use R or M? Or did I? Yeah, I use M, right? Yeah. Sorry. Yeah. Yeah. So here we have a P M bar N L by Q. Okay. So that's the part modulo Q, which more or less like what we had before. And then we have a sum over P, which is little involved. It's not just tau sum. We have a chi bar of M minus A L. And then you have an E of minus A Q bar N by P. Okay. It's easy to show that this is bounded by square root of P. That's easy. But yeah, in the next step, we'll have we have to do something more than just square root of P. Okay, so outside I have a sum over L and a sum over N, and there's a sum over M, there's a sum over Q. L, N, M, Q. Okay, so now the next step is so far, if you count, do the computation, you will say that so far we have saved yeah, so you say P to the power 3 by 2, sorry, yeah, for the P to the power 3. So you have saved P root L, okay, which is like N root L. So our target was to save N times L, and so we are not really at the threshold. We have saved N root L, okay. Previously, when it didn't do this, all this trick thing, we were at the threshold after applying the summation formula and before Cauchy. So now we are away from the threshold, but we are in a better position, as you would say. Okay, so I'm going to take the large sum outside. So the large sum is N, which is still of size P. I'm going to throw in my L, M, and Q inside. And then there is this the character sum over here. And then you have a E of P, M bar, and L, Q square, right? Oh, yeah. So now again, the last step, as usual, is open the absolute value square and apply Poisson, right? Now, when you apply Poisson, there are two things. That one is the zero frequency, which will reflect the diagonal contribution, and there is the non-zero frequency. So the saving that you get in non-zero frequency is the initial length by square root of the conductor. So when we open up this thing over here, the conductor is P times Q1 times Q2, because there will be two Qs, Q1 and Q2, but the conductor of this sum remains the same because P is fixed. Okay, but if you look at modulo Q, then it is just an additive character. So if it is an additive character, you save more. It's like a geometric series. You save the whole length. Okay, so the saving will be P by square root of P. Okay, so it will be just square root of P. Okay, because for modulo P, it will give rise to a complicated character sum where you have to apply the Deline's result and get square root cancellation there. And that and for the other part, this part, it's just a geometric series, and you save the full length. So the saving is p by square root of p, which is root p. All right. So that's the non-zero frequency, and at the zero frequency level, that's the same thing as the diagonal. So we have to just count how many elements we have inside the diagonal. So that will be L, the number of elements inside the absolute value over here, L times M. So M was of size what? M is of size Q. And then you have another Q. And then if you go back, so this is the number of elements you had. Our choice of Q was root L. Right? So we're going to save Ln, so it will be L squared. Okay, so that's the amount we save in the zero frequency. Okay, so what is the optimal choice? The optimal choice will be just equate the diagonal and off-diagonal saving. So optimal thing is L squared equals to root P, or L equals to P to the power 1/4. Yes, that's our optimal choice for the mass transfer, the amount of mass you want to transfer, that's P to the power 1/4. And so let's go back. So before Cauchy, we had saved n square root of L. And now we have said L squared after Cauchy. So we have to go back and take square root of that. So this is the total saving we have. So that is n L to the power, or maybe, yeah, that's right, NL. That's the amount that I need to save. This is the extra that I have saved, right? So it's NL P to the power 1/8. Okay, so this is the extra saving. Okay, recall that in the previous approach, the extra saving was P to the power 1/116. That has come down to P, that has grown to P to the power 1/8. Okay, so from here we get that L half F twisted by chi is bounded by P to the power 1/2 minus 1/8, which is P to the power 3/8, which is the Burgess bound. Okay, so it's one of the classical bounds that we have. Okay, so by applying the template with a little trick, you can actually get very strong results, like classical results that we have. Yeah. So now let me list the problems that one can try to solve using this template. Of course, the one thing is the subconvexity problem. This is the main problem I'm really studying, but yeah. Okay, so in the subconvexity problem, you're basically interested in the L function. For the L function, you have an approximate functional equation, and that gives you an expression of the L function inside the critical strip. And that expression is looks like the sum S that we had before. In fact, if you're looking at Rankine-Selberg convolution or twists of some form, then that will be exactly equal of the form S that we are studying. Okay, then other type of problem that we're interested in are called shifted convolution sum problems, or this additive divisor problem. Here I've written down one such problem for GL2. So lambda Fn and lambda Gn are the Fourier coefficients of GL2 modular forms of mass forms. As I said, that it appears, this type of sums appear also in Dirichlet divisor problem. So if you're looking for dk, so it's the kth order divisor function, but d2 is the usual divisor function. Then if you look at, so there will be a main term and then the error term, and you're interested in the error term over here. The error term has an expression of this type. Okay, and so here, this is what's called the nonlinear twist. Okay, so it's nx to the power 1/k, and you need to get some non-trivial cancellation of this where for n in certain range. Okay, so the initial length of the sum was x, and now it after applying Voronoi, it gets transformed into a different length, capital N, and x is reflected. X pops up in the exponent over there. You can also look at the cuspidal analog of Dirichlet problem, which is trying to bound this sum with a sharp card. So you're taking all n's up to x and no n's after that, and whatever you're taking, you're counting them with weight 1, and whatever you're not taking, you're counting them with 0. Okay, so that's the sharp card thing. This is the analog of the Dirichlet divisor problem, and again, In this case of the Voronoi, you are left with analyzing sums of this type. This is called nonlinear twist, like before. And here, this n will be of size x to the power 1/3. Right? So we need to get, so if you can get a non-trivial bound for this sum for n of size x to the power 1/3, then you get a non-trivial bound which will be better than x to the power 1/3. Okay? This is the bound that we are looking for. X to the power 1/3 is known. Okay, so the other thing is if you're interested in critical zeros of symmetric square L function, okay, so this is a GL3 L function. So you take a GL2 form, look at the symmetric square L function on that. That's a GL3 object. And for those, it's not known whether any of the zeros are on the central line, where the Riemann hypothesis still says that all the zeros are on the central line, but we don't even know that a single zero is on the central line. Okay, the problem is that you have to estimate sums of this form in this, and it's so here also it's non so a is some constant over here. It's not related to anything, so you can take it like 2 or 3. It's just fixed number, and then you have a nonlinear exponent into the power 2/3, and you're looking at nonlinear twist of a GL3 form, and you can get non-trivial bound for this sum, but you need a saving of n to the power 1/6, which is asking for a saving of wild strength, the GL3 level, okay, which is quite difficult. If you're interested in a simpler problem, or if you're interested in a problem which looks simpler, you can look at the linear twist of GL3 form, and the best bound that's known so far is n to the power 3/4. So if the conjecture is it's bounded by n to the power 1/2. So this is also of the form that we are interested in. Okay, so I'm going to now list some of the results that have been proved using the template. Okay, first, of course, for subconvexity problem in the GL3, so I use this approach to get the t aspect subconvexity. So it's pi is a GL3 form over here, and so it's in the t aspect. The t is going to infinity. Pi is fixed. T to the power 3/4 is the convexity exponent, and I have a saving of 1/16 over 3/4. One can try to improve it, and it's possible to improve it. The next thing I did was the GL3 twist aspect. So here I'm looking at the central value. Pi is fixed, but it's getting twisted by a character modulo p. Okay. Again, p to the power 3/4 is the trivial bound, and I have a bound p to the power 3/4 minus 1 by some number which is 3-digit number. But you can improve that, and people have improved that exponent. So I'm not going to mention what I had. Okay, as you saw, I proved the Burgess bound using that trick for GL2. You can use the same thing to prove the Burgess bound for GL1, the usual Dirichlet function. You can use the same approach to get the wild bound for GL1 form and GL2 form. And also, if you look at the GL3 plus GL2 Rankin-Selberg convolution, and I use the same approach to get the t aspect bound for this degree 6 L function. So that was the last thing that I did. Okay, so but my students and postdocs are also working on this type of problems, and they are getting beautiful results. First is Sharma. So he looks at GL3 plus GL2 in the twist aspect. So he takes a GL3 form twisted by a GL2 form, twisted by a GL1 form. It's again modulo p. This guy is modulo p. The conductor is p to the power 6. So p to the power 3/2 is the trivial bound, and he gets an improvement over that. And I don't remember what improvement he had, but it was a non-trivial improvement. My other student, Kumar, he's looking at, or has already written this. Sharma has also finished writing this thing. These are already in the archive. So he looks at GL3 plus GL2, and the GL2 spectral parameter varies. Okay, so you can, for example, you can assume that the GL2 part is a modular form f of weight k, where k is going to infinity. Okay, so then if you look at this Rankin-Selberg convolution, there are 6 gamma factors in this in the functional equation, and so the conductor is like k to the power 6. So k to the power 3/2 is the convexity, and he gets a subconvex bound in this case. Okay, and then there is a paper by Kumar, Malesham, and Singh, and they look at the GL3 spec. So they look at the same GL3 plus GL2 Rankin-Silber convolution. Their GL2 is fixed. The GL3, the spectral parameters of GL3 vary, and they get a non-trivial bound or subconvex bound where, interestingly, the spectral parameters are near the walls of the Weil chamber. Okay, they are not in the generic location. Yeah, but you can use the same type of approach to get subconvex bound also when they are not near the. Okay. So the last thing I want to mention is this thing about nonlinear twist. I really don't have much time. So this is the problem. It's quite interesting. So you have Fourier coefficient. So you have a GLD form. So if you don't like GLD, you can take D to be 2. So it will be a modular form. Then you can ignore these ones over here. So that is lambda n. That's a normalized Fourier coefficient of a modular form. If you take D to be 3, then you have a lambda n1. That are the normalized Fourier coefficients of a GL3 form. And in general, for GLD, there will be D minus 1 terms over here. So there will be D minus 2 many ones over here. And this n is varying. Okay, and we're interested in the sum of this sort, an e of n to the power beta. Okay, so the conductor of this sum is n to the power d beta. Okay, so that's the conductor. That's the complexity. So basically, this sum becomes interesting when n is smaller than n to the power d beta by 2. Okay, so we draw this line. So this is going to be my beta line. Okay, so that really means that if beta is larger than 2 by d, okay, so in this range, if beta is in here, then the problem is kind of trivial. Do not worry about it. When the beta is over here, then it is non-trivial. Okay, and it means that no bound is known for beta in this range, or no non-trivial bound is known for beta in this range for d greater than or equal to 4. Okay, so for 2 and 3, we know non-trivial bounds. For 4 onwards, we don't have any non-trivial bounds. For the next point mark over here will be 3 by d. Okay, and so this is like the Weil mark. So if you are taking beta larger than this, then you are really going inside the sub-Weil region. Okay, so that will be the very interesting range. For GL2, it's known that you can go up to here. So you can reach the Weil boundary. You can cross the this is the convexity barrier. So you can cross the convexity barrier and go up to the Weil barrier. Okay, so we know non-trivial bounds for beta going up to here. For GL3, we do not know that much, but there is a recent result due to my student and postdocs and my former postdoc. And they get a non-trivial result for d equal to 3. So their beta goes up to 3/4 plus 3 beta by 10. So this is the bound. So beta is here. So you get a non-trivial bound for beta less than 5 by 6. Okay. And so for d, so 5 by 6 I'm sure is somewhere over here. Okay, so if d equals to 3, then it is 2/3. And they improve the trivial bound to something non-trivial bound. And here they use the same trick and the method that I applied in my proof of p aspects of convexity for GL3 L functions. So I don't have much time. I don't really have any time. So I'll stop with that. I'll not try to give any indication how to prove this result. Their paper is in the archive and you can read it from there. So with that, thank you.
Thank you, Ritabrata. It's a beautiful talk. I think a lot of people are here, students are here, will be really benefited from this talk, and all of us will be benefited too. Is there any question from the audience? I think you have given such a beautiful talk about all sides. No, it's a really nice talk. And
Oh, thank you.
thank you.
Thank you.